all of you understand the idea? Okay. Let me now kind of start sharing some, let's talk about a core idea in statistics. That's a very important idea. Probably one of the most significant ideas in statistics is what I'm going to talk to you about now. It is the idea of a random variable, right? Anybody, that's really at the base of everything that we do in statistics. Has anybody ever heard this term, random variable? What is it? You all heard, but what is it? Can somebody give a quick definition of a random variable? Yeah? To define a random variable, you need to talk about what is called an experiment of chance. What's an experiment of chance? It's an activity. By experiment, don't think you're going to go into a lab and with those lab coats and have some rats and give medicines to some rats and not to others. Not that kind of experiment, right? Okay. Any activity that you do, all whose outcomes are known to you in advance. So if I do this, then A can happen, B can happen, C can happen, D can happen, but you do not know which of them will exactly happen. Right? If you have, so an experiment of chance is simply an activity which has different possible outcomes when you do it, right? You know what all the possible outcomes are, but you can't predict any outcome in advance. For example, a one-day match between India and Australia has, what are the possible outcomes? Win, lose, draw. Right? Win, lose, tie. But can you, before the match starts, ever predict that one of these outcomes will happen? Unless you're a bookie, right? Okay? Sure? But nobody normally can predict what exactly the outcome would be. That's an example of an experiment of chance or a chance experiment. Give me more examples of chance experiments. Rolling a die. Okay, rolling a dice. Why is it a chance experiment?
Because we know the outcomes.
What are the outcomes? 1, 2, 3, 4, 5, 6. But you can't predict which of the outcomes will happen beforehand, right? Before you roll the die. Once you roll the die, you know what has happened. But before you roll the die, you never know what are the possible outcomes. Give me more examples. Exam results, yes. Right? So you may pass or fail, but you really can't predict 100%. Right? Speaks a little bit about our examination system, right? But yes, so you can never be sure about whether you pass or fail. Any other example of a random experiment? Coin toss. So outcome could be head or tail, but I don't know which of them, right? So there are these many random experiments of chance or chance experiments, right? Where you know the set of all possible outcomes, right? But you do not know what specific outcomes. So the key point is that you have to know all the possible outcomes. Yeah? Right? Sure? Now, okay. Suppose now these outcomes get numbers associated with them. Example, if I roll a die, the outcomes are numbers. 1, 2, 3, 4, 5, 6. If I toss a coin, the outcomes are not numbers. They are H or T, no? Head or tail. Pass or fail are not numbers. Right? Okay? Sure? Right. So, random experiments or experiments of chance where outcomes are numbers, right? We'll focus on them. And the outcomes of such experiments of chance, if you have an experiment of chance where the outcomes are numbers, then such outcomes qualify to be called as random variables. So random variable is a numerically valued outcome of a chance experiment. Right? Some outcomes, some random experiments which don't have numerically valued outcomes. For example, tossing a coin. The outcomes are not numbers, but I can easily convert them into numbers. For instance, if you play a game, if the coin is tossed and if it's heads, you get 1 rupee. If it's tails, you give me 1 rupee. So if it is heads, the outcome is +1. If it is tails, the outcome is -1. So I have been kind of being able to reassign the non-numerical values into numerical values, right? And I can convert it into a numeric valued experiment, and therefore all those can also be looked at as random variables. Is this clear? The idea of random variable absolutely clear to everybody? All right? Okay? Sure. Now random variables can be discrete or continuous. For example, if I roll a die, the outcomes could be 1, 2, 3, 4, 5, 6. The outcome would never be 1.234578, no? Because that number is not there on the uppermost face of the die. But if I ask you how much time does it take, suppose my experiment is coming from Y to Pune, like I come every Sunday, right? And the outcome is the time taken for coming from Y to Pune. Now the point here is that what is the time taken to come here? The time is not really 2 hours 30 minutes, it's 2 hours 31 minutes, 2 hours, not even 2 hours 31 minutes, 2 hours 31 minutes 7 seconds. Probably it's not also 2 hours 31 minutes 7 seconds, 2 hours 31 minutes 7 seconds and 99 nanoseconds, but this is also more than that, right? Sure. So really if you have some outcomes where you can't talk about a specific value, then we talk about the outcome as time taken lying between say 2 hours and 2 hours 5 minutes, 2 hours and 2 hours 10 minutes, right? But those still numeric valued random variables, right? Okay, so those random variables are called continuous random variables. So you have a discrete random variable, you have a continuous random variable, right? For example, if if I go to like next Thursday, I will go to a place called Lonand. Do you know what is Lonand famous for on Thursdays? Animal markets, right? There are goats and sheep are all being sold, right? And there are lots of sheep there, and if I pick up a sheep at random and think of the weight of that sheep, so the weight of a sheep picked at random from a lot of sheep sitting there, aram say, right? Will that be a discrete random variable or continuous random variable? The weight of a randomly picked sheep. Continuous, right? So I can only think of it lying between some two values, right? Okay, sure. But if I think of the number of sellers who have come there on any particular day, number of sellers who are in the Lonand sheep animal market on a particular day, not all sellers come every day, no? Right? Some sellers come, sometimes you don't have any sheep to sell, sometimes you have, right? You have other work, etc. So the number of sellers who are there in the Lonand sheep market on any particular day, is it a discrete random variable or continuous random variable? Discrete random. Perfect. So I understand. Now I'm sure you get this idea, right? Okay, now we are going to play a game. Okay, right? We are going to play a game and we are going to see a very interesting idea. I'm going to go to a little bit of R and do some sampling and all that kind of a thing. Yeah? Sure? Okay. So now, friends, I'm sharing my screen for you. Are all those online folks, have you understood the idea of a discrete random variable, a continuous random variable and so on? Yeah? I hope you have, right? Somebody is wanting to come in, I think. Oh. Yeah? Sure? Everybody's got this idea? Okay, now I'm sharing my screen with you. Pardon? Yeah, Pallavi. I can't hear you properly, Pallavi. Can you please be closer to the mic? Yeah.
Am I audible?
Yeah, Pallavi. Wonderful.
Okay. Okay, so let's like if we define a variable called age of individuals, right, in years. So if you are instead of complicated, so that will be this way. But let's say if you are saying like 7 years, 5 months, no, will that be complicated?
Well, if you round off the age, it will be a discrete variable. If you don't round it off, then it's a continuous random variable, no? Because your age really some years, some months, some dates, some hours, some minutes, some seconds, some nanoseconds, some nanoseconds, and so on. Right? So it will be a continuous random variable, correct? Yeah. Sure? Okay, so I'm now sharing my screen. Yeah. Yeah, hold on. Oh, baby Sunanda. Admit all. Yeah, everybody admitted now? Okay. Okay, now I'm sharing Excel. Can everybody see the Excel sheet now? Is a blank Excel sheet visible to everybody? Yeah? And suppose now I'm going to play a game with you. Right? I'm going to toss a coin. And if the coin turns up heads, you get 1 rupee. If the coin turns up tails, you lose 1 rupee, right? And if I toss the coin 5 times, the first toss was a head. So how much should you get? 1 rupee. Second toss was a head. How much should you get? Third toss was a tail. How much should you get? You lose 1, right? Minus 1. And then 1. Correct? Okay. Now, so how much did you earn in all from playing this game with me? 1 rupee. 1 rupee over all the 5 games. Right? How much did you earn per game? If you want to find average earnings per game, you'll have to sum all the earnings and divide by 5. Right? Sure? So what I'll have to do is, I'll call that X bar. Please, I'm going to do some very elementary stuff. So please pardon me but this requires to be done. Okay? This is the total I have, plus 1, minus 1, minus 1, minus 1. Right? Sure? To obtain the average, I must kind of add all this up and divide by 5. Right? That can be written as 2 into 1 plus 3 into minus 1 upon 5. Yeah? Yeah? Sure? That can be written as 1 into 2 upon 5 yeah. There are 2 minus, no, there are 3, oh sorry, there are 2 minus 1s, you're right. So this should be 3, correct? And this should be 2, yeah? 3 positive ones and 2 minus ones, right? So I can then rewrite this as 1 into 3 by 5 plus minus 1 into 2 by 5. Yeah? right? This is the mean, right? I will call x bar, the mean of this particular outcome. I can think of it as a sample, right? If I toss the coin 5 times and I get some numbers, I can think of the sample and consider x bar as this, right? Now remember, what is 1 and what is minus 1 in this case? These are the outcome. Those are the values of the random variable. Plus 1 and minus 1, right? What is 3 upon 5? No, it's not probability. What is 3 upon 5? Why have I written 3 upon 5? Because I tossed the coin 5 times, out of it there were 3 ones, right? 3 upon 5 is called the relative frequency of 1. In this sample, the total frequency is 5, out of which 1 has occurred thrice, right? So 3 upon 5 is the relative frequency of 1. And what is 2 upon 5? Relative minus 1, right? So please remember, when you think of the sample mean, is nothing but each value that the random variable takes multiplied by the relative frequency with which it takes it. You multiply this each value by the relative frequency and then add all of them up. Then you get the sample mean. So sample mean is nothing but a weighted average of the different values with which a random variable occurs. Yeah? Is this clear? Right? So sample mean is nothing but each value of the random variable multiplied by the relative frequency with which those values occur, and then you finally sum it. Correct? Right? Everybody gets this? Sure? Okay. Now I am going to ask you some questions. Now here my x bar is, so if I do this, it turns out to be 0.2, correct? Yeah? Now, suppose instead of playing this game just 5 times, I play this game 500,000 times. If I am just playing this game just once, or 5 times really, only 5 times, I play this game 500,000 times. So 500,000 times, I roll a die, I toss a coin, and we keep on playing this game. Do you think x bar will still, what do you think will happen? How do you think the results will change? Okay, he says x bar will be close to 0. Why?
Because we are tossing a coin and it is symmetric basically, our experiment. That's why we get as many positive values as
Okay. He's saying something fundamental, but I want you to kind of add to it. He's saying that because the coin is a balanced coin, we played 5 times, obviously there will be either 3 ones and 2 minus ones or 2 ones and 3 minus ones. 5 times here. Right? Sure? But if I do this, keep on doing this more and more and more often, will I still get 1? If I still get a head 3 by 5 times, so 3 by 5 is 60%. So if I keep on doing this more and more often, will I continue to get a head 60% of the times and tail 50% or 40% of the times, or something else will happen?
50%?
Close to 50%. So if I keep on tossing it more and more and more often, right, okay, the percentage of heads should get closer and closer to 0.5. Percentage of tails should get closer and closer to 0.5, right? So actually now do that, right? Okay, so 1 star, right, 0.5 plus minus 1 star 0.5. This is a number that it should get closer and closer to, right? And what is this number? What is 0.5 into plus 1 plus 0.5 into minus 1? Do it on a calculator. It will be 0, right? Okay, now we have learned something fundamental. As the sample size increases, right, in this case, the sample mean x bar will tend to get closer and closer to 0 because the relative frequency of a head and the relative frequency of a tail will both get closer and closer to 0.5. And what is 0.5? 0.5 is nothing but the probability of a head. 0.5 is nothing but the probability of a tail as well, because if I toss a coin, I have no way of saying whether the coin will actually land heads or the coin will actually land tails. So, a 50-50% chance it will land either way, right? And actually if I keep on doing this many times, that's where the relative frequency will converge to, get closer and closer to, right? So, we learned two things. The fraction that the relative frequency of an event tends towards, as the number of times we do the experiment increases, is called the probability of that event, right? The frequency, the fraction to which, yeah, the relative frequency of an event tends to, as the number of times we keep on doing the experiment increases, is called the probability of that event, right? So, in effect, what we are calculating is 1 star probability x is equal to 1 plus minus 1 star probability x is equal to minus 1, where x is the outcome of a, yeah, sure, okay. So, 1 is the outcome, minus 1 is another outcome. P of x is equal to is the probability x is equal to 1. P of x is equal to minus 1 is probability x is equal to minus 1. And then if you do this, what you get is a value called the expected value of x, right? A value called expected value of x, right? So, you will now clearly see that as the sample size increases, the sample mean tends to the expected value of x. Is everybody getting this? If you are getting this, we must all eat one chitale laddu, because we have learned a very important idea in statistics. This idea is called the weak law of large numbers, right? Very fundamental to statistics, right? I'll tell you why, right? It's kind of one of those, have you seen those stone bridges with arches? And there is one stone in the middle, and if you remove that stone, the arch collapses. That stone is called the keystone, right? So, one of those keystone ideas of modern statistics is the weak law of large numbers, which says as the sample size increases, the sample mean will get closer and closer to the expected value. And why does that happen? That happens because the relative frequencies of events will get closer and closer to the probabilities. And by definition, the expected value is each value of the random variable multiplied by the probability and summed. The sample mean is each value of the random variable multiplied by the relative frequencies and summed. So, as the relative frequencies get closer and closer to the probabilities, the sample mean will get closer and closer to the expected value, right? Sure? Is this idea clear to everybody? If this is not clear, then you will not know good statistics, right? If it is clear, intuitively obvious, okay, the proof for this is not so obvious, we will do this intuitively, right? Okay. Of course, it requires all the experiments to be identical and independent, right? So, what happens on one toss of a coin should not affect what happens on subsequent toss of the coin. So, in each case, we want the outcomes to be 1 minus 1. The experiment's essence is not changing, right? So, all those random variables are identical random variables, yeah, and the experiments, outcomes of one experiment have nothing to do with outcomes on the past or future experiment. Every time you toss a coin has nothing to do with what the past or the future will do. These are called independent, right? So if you have a sequence of independent and identical random variables, then the sample mean will get closer and closer to the population mean. Yeah? Sure? Okay, remember, now let me ask you a question. Suppose you are a gambler. The game is toss a coin, and now the stakes are high, right? Suppose you win, you get 5,000. If you lose 5,000 rupees. And you lost 4 games in a sequence. You lost 20,000 in the last 10 minutes, right? 5,000, 5,000, 5,000, 5,000. Do you think that the next toss, because you have lost 4 times in a sequence, you are more likely to win on the 5th toss? No, because the tosses are independent of each other. Coins don't have memory, right? Coins don't have memories, right? And such professors have very nice names in statistics, martingale, Markov chain, and all kinds of things, right? So let's not go into that, but that's how, right? Okay. So understood the idea? Sample mean gets closer and closer to the population mean, right? Why population? Because what you're doing is, if you have an infinitely large number of trials, then you have the population. Now, why is this important? Suppose I asked you, or for some reason somebody asked you, there is no reason why you should do what I ask you to do, right? Suppose somebody asked you to find out the average income of a person in Pune. How much does a person in Pune earn on an average? Right. If you really wanted to find out the real, actual number, then you'll have to catch hold of every person. You'll have to define something, right? Some number. How much did you earn last 1 week, for example? You'll have to ask the person, how much did you earn last 1 week? This is something, you write it down. You ask all people in Pune this question, right? Including babies and including old people, right? Because you want that number, right? And then you put all that into an Excel sheet and take the average. You'll get some number, no? Assuming everybody tells you the truth, right? So you have a big sack of truth pills. So catch your sampling method is you catch anybody, truth pill, how much did you earn last week? He corrects the right number. You go catch the next person, truth pill, right? Okay. So you find out like that, and then you have, and suppose that number comes out to be 1,600 rupees. Right? So it means that the average person earns 1,600 rupees in a week in Pune. Right? And that would be average for all the people in Pune, including babies and old people. Right? So that would be the population mean. Will that be a random variable? No, because if nothing happens, if you do the same thing again tomorrow, again catch people, give them truth pills, ask them questions, right? And they again tell you the truth, right? So you get all this, you'll get the same number the next day. So it's not an outcome of a chance experiment. You can predict beforehand what the exact number would be. The population mean is not an example of. But can you actually do this? Can you actually catch hold of everybody in Pune, every single person in Pune, right? Right? Put him or her into a narco test and find out what the earnings are, right? Sure? Can you? You can't do this. So what will you do? You will take a sample, and you will definitely not give narco test to your sample, right? You will ask them and hope they tell you the right answer. So you will take a sample. Suppose you take a sample of 1,000 people. So that sample, suppose I am there, he is there, she is there, he is there, right? And we get a sample. And you ask us, and you get a number called, say, 1,162. Is it the same thing as the population value? No. Why? Because if you take a different sample from the same population, you will get a different number, right? So if he does the same exercise and she does the same exercise, you'll get a different number, right? So effectively what you have is a continuous random variable, outcome of a continuous random variable, right? Okay, and each one of you will get a different answer because you have a different sample. Now you see the problem. We are not interested in what you get in the sample. We are using the sample because we want to know what the population is, right? Yeah, somebody shows me a photograph of Charles Shobraj because they want to catch him. I'm not interested in the photograph. I'm interested in what the photograph tells me about how Mr. Shobraj actually looks like, right? So we are not interested in the sampling estimates per se. We are interested in what the sample tells you about the actual population value. Correct? So every time you cook at home and you want to see whether the rice has been cooked, you take out some little bit of rice and then taste it, or at least whether you say whether there is salt is proper in the curry, right? You actually taste a little bit of it, but you are not interested in how that spoon tastes. You are interested in whether they actually saw how that curry tastes, right? So you are interested in the population numbers and not the sample numbers, right? Now you know that sample numbers are a completely different thing. They are random variables, and population numbers are not random variables, they are fixed numbers. So the entire animal is different, qualitatively different. The information that we have is qualitatively different. What we want to know is qualitatively different from what we have in our hand. Yeah? You see the big problem? I have done a survey, and my survey tells you that per capita income in Pune is 1600, but he did it and he found it to be 2100, and she did it, she found it to be 800. Now what is the reliability of our surveys? Right? Why should we even believe those surveys? Right? The first thing, so the whole science which deals with this, of going from surveys, from estimates to the actual numbers that we want to know, is called the science of statistical inference. Okay, right? So we have only limited information. That information, on the basis of that information, we make a guess about the true value of a population parameter. The population parameter is not a random variable. Our guess is a random variable which depends upon our information. The people who come into my sample are actually my information. So if the people who are coming into my sample change, I will get a different estimate. My guess will be different, right? We are not interested in the guess, we are interested in how good the guess is, or what is the relationship of the guess with the population parameter that I want to know, but I have no way of knowing directly. So the weak law of large numbers tells you something fantastic. It tells you that, look, your sample mean will be different from the population mean. But provided you do your sampling correctly, that is, your sample elements are independent and identically distributed, then as the sample size increases, your estimate will get closer and closer to the true population value. You might never know the population value, but you will still get closer and closer to the true population value. Yeah? Right? This is the only link we have. And then we can ask a question, okay. So you can now ask me a question, okay sir, so that's we agree with you. So suppose the sample size is this much. How close am I to the population value? That's where I can start answering questions. Right? Then I can say, okay, you are likely to be around this confidence interval. You are likely to be around 5% here and there. Right? Within your true value is likely to lie within, say, these two with 95% probability. I can answer questions like this. But I could not have been able to answer these questions without the weak law of large numbers, which makes sure that as my information quality increases, right, my guess gets more and more correct, close to the true answer. That is the weak law of large numbers. Yeah? Sure? But of course, it's not only about the quantity of information, it's about the quality of information. Why? Because I want all the samples to be independent and I want them to be identical from the same process. Right? So I can't add some, so it says that I can't ask people from the same family about how much the family earns and if I'm asking more. So I can't go to a college and call all college lecturers who have just joined last year, who have just had 1 year of service, and ask them how much you earn, how much you earn. I ask 50 people like that, I have 50 data points. No, I have only one data point. Because all of them will have exactly the same income. Right? So it's not the quantity of information, it's the quality of information. Right? It's the quality of information. Is this clear? And independence. Right? So if I want to find this from Pune, right? There are some people who have come from Delhi and who want to be there only for 1 day. Some very rich sheikhs are visiting Pune, right? A contingent of sheikhs are visiting Pune, right? The whole of sheikhs of Dubai have come to Pune just for 1 day, right? To meet me, right? Okay? And they are going to go away. You can't sample them because they are not the identical process. They come from a different population, right? Okay, so as long as your quality. Now that brings me to a very important concept in statistics called the degrees of freedom. Degrees of freedom. Have you heard of this concept? Yeah? What is degrees of freedom? Tell me.
Sir, I'll try.
Yeah. Intuitively, yeah.
So, if I have 10, if I have the average, and if I have, say, 10 of my samples based on which I am having the average, if I know the 9 numbers, I can know the 10th.
Yeah, okay. She's right, but let me give you a wider example. Suppose I want to find what is the time exactly, right? My watch is 11:11. But I'm not, why should I think that's the exact time, right? I might be 1 or 2 minutes fast, right? So I ask him, what's the time? And he says 11:14, right? If I am, now the point is, if I'm saying, if I'm just relying on my time, 11.11, right? I might be quite wrong. If I think of this as the right time, I might be here and there, right? So the variance of my estimate, I want to estimate the time. The variance of my estimate might be quite large, right? The true value might be somewhere and my value could be lying here and there, right? Much variance could be large. Now, suppose I ask Vijit, how was the time? And Vijit says it's 11:20. So I say, okay, I have one information 11:11, one information 11:20. I have 2 bits of information. Let me use both of these 2 bits of information into, and by converting them into 1, I take an average. So what do? 0.5 into my estimate plus my information plus 0.5 into Vijit's information. I have now 2 bits of information and I am giving equal importance to both, right? Because 0.5 into mine plus 0.5 into Vijit's. I am giving equal. So I am now basing my estimate on 2. I have doubled the information. So the estimates will become twice as precise, right? As it would have been if I was using only my, because now my information is double. If my information is double, my estimate should become twice as precise. Is this clear? Now if I ask Pooja as well, Pooja says it's only 11:05 in my watch, right? And if I now average all 3, I am using 3 bits of information. So the precision of my information will be thrice compared to what I am using only when I am using only 1 bit of information, right? So I have 3 bits of information here. But now if Pooja tells me that, sir, because I come with you, no, so I am going to fit my watches exactly according to your watch. So the time in Pooja's watch will just be, she says, I put it 5 minutes faster than you, right? So if I know time in my watch, I know time in Pooja's watch. Or if I know time in Pooja's watch, I know time in my watch. So either her information is redundant or my information is redundant. So I really don't have 3 different points of information. I only have 2 different information points. So my degrees of freedom in this case are not 3 but only 2. Right? And what matters for an estimation is the quality of information, the independent bits of information I have in order to form an estimate. Right? And that is what you call degrees of freedom. It is the amount of information, independent bits of information that you have in a sample which help you to, which are useful in estimating a population parameter value from the sample. That is what you call degrees of freedom. Sure? Right? Okay? Everybody gets this? Okay, wonderful. Right. Okay, now, so this is clear. Law of large numbers is clear. Information idea is clear. And the idea of degrees of freedom is clear. Yeah. So suppose I have n data points, n bits of information. From these bits of information, I want to find out, right, the value of a population parameter. Now it's possible that all these n data points give me independent information, standalone information, which is not given by other things. Then I have n degrees of freedom. But if, say, 2 of these bits of information can actually be derived from the rest, then I have only n minus 2 degrees of freedom, because those are the only bits of independent bits of information that I have. Yeah? Like for instance, if I ask him what city this is, he says Pune. If I ask all of you which city this is Pune, right? Asking more people is not adding information. Right? It's not the sample size. Right? Or if I ask him, what is the temperature in your city today? He'll give me an answer. You'll also give me the same answer. You'll also give me the same answer. Right? But if I have to ask him a question, ask somebody in Delhi another question, ask somebody in Melbourne another question, ask somebody in Helsinki another question, then I'll have independent bits of information. Here, asking one person in Pune what is the temperature right now, right? And asking everybody in Pune what's the temperature right now will give you the same answer, assuming all of them know the temperature correctly. Right? And so, asking all people in Pune what is the temperature is not an increase in the sample size. Because even if the sample size could be 500,000, the useful information is only one bit. One of them is correct, that is enough. Yeah? You see the points of degrees of freedom? So that's why statisticians worry so much about degrees of freedom. Your teachers must have also told you that degrees of freedom are very important, but unfortunately they never defined what those degrees of freedom are. So everybody is left worrying, sir, should it be n minus 1, should it be n minus 2, should it be n, right? Okay? It's basically the number of data points that can vary independently. Right? Like for example, in the time example I gave, he can set his time as he feels like. If I set my time to something, then Pooja has to set it 5 minutes faster. If Pooja sets his time as something, I have to set it 5 minutes slower. Because that's the rule, right? Her watch is 5 minutes faster than me. Which means that only there are two data points which we can vary independently. The third has to dance to the tunes of the other two. Right? Sure? So, degrees of freedom idea is clear? Right? Okay. So, central means limit theorem. Now, this is really the most important property. That's why all of us in statistics, you will see all the estimators that we use are in some way or another means. And that's why they go to the population mean. That's why we don't use the median or the mode so much, even when we think that the median might be a better description of reality. So, for example, the median might be a better description of income in Pune compared to the mean, because the mean is, is influenced by high values, right? If you go to Pedder Road, for example, in Mumbai, the mean income would probably be some number which I can't even, how many zeros, I don't know where there is, right? Because there is Mr. Ambani's house there, and Lata Mangeshkar used to stay at the other end. But there are also a lot of poor people who say, there's a hospital out there, a lot of people who sell coconut water, nariyal pani and flowers and chai and those kinds of things there, right? But those numbers will never represent them, right? So the idea is to take a median. Median tells you 50% of people have income below, but the problem is that the median doesn't have this property. So going from the sample median to the population median is very difficult. Whereas the law of large numbers tells me that from mean, sample mean, you can go to the population mean. Right? So all the estimators that we use will be actually in one form or another, means. Right? The law of large numbers is another important property. If you take a sample mean, if you take another sample mean, and if you take the ratio, then as the sample size increases, this sample mean will tend to the ratio to the population mean, this sample will tend to the population mean, and the ratio of the sample means will go to the ratio of the population means. Right? That's a very pretty property, going to be very important for us. Is the idea clear now? Mean is clear? Okay. Now I am going to ask you another stupid question. Right? A rather stupid question, but I don't have a blackboard here, but I'll just try kind of write it, show you here. Right? So, suppose now, I'll try to do this in Word. I hope I can do this in Word. Okay. So, we are thinking of a city, right? How do I get a straight line? Okay, forget it. I can just get a straight line here. So, this is everybody sees a straight line? Okay. So, this is a road. Okay. This is the road begins, so it's milestone number 0. Okay. This is milestone number 1, right? And your house is bang opposite milestone number 1. Okay? This is milestone number 2, and your friend's house is exactly opposite milestone number 2. Right? This is where the city begins. Mumbai 0. Right? Sure? Sometimes if you go to Nagpur, yeah, there is a 0 point in Nagpur. Do you know what it is? Center of India, right? Okay, that's where all the distances start. So that's a 0 point for the whole country. Right? There are lots of 0 points in Nagpur, but that is more important one. Okay, so this is 0. Right? So this is y, right? 1 kilometer. So these are kilometers. F is 2 kilometers. Right? Okay. Now, if I ask you the distance of your friend's house from your house, what would that distance be? 1 kilometer. Everybody agrees? Anybody disagrees? 1 kilometer, right? Okay, so this is your friend's house, this is your house, milestone number 2, milestone number 1, your friend's house to your house. How did you reach that conclusion? She said 2 minus 1. So if I asked her to calculate the distance of the friend's house from your house, you take the milestone on your friend's house, subtract from it the milestone on your house, 2 minus 1. Now think of it as a computer. I am now asking you the distance of your house from your friend's house. What will you do? So if you find the distance from F to Y, take the milestone in front of F, subtract from it the milestone in front of Y, you get the answer, F to Y. Right? What is the distance from Y to F by the same logic? 1 minus 2 minus 1, we are in trouble already, because we are saying this is a straight line. This distance cannot differ from this distance. Distances cannot be negative. Right? Okay? So what to do? How to solve the question? What would your solution be? Absolute value. That's the most sensible thing to do. Right? Okay? And there is another one which is not very satisfactory, but you say 2 minus 1 square. So 1 minus 2 square is the same answer, 2 minus 1 square is the same answer. right? The second answer is not satisfactory. The second answer is not satisfactory for the following reason, right? There is, suppose, a third friend of yours who lives here, right? Say 3, right? Say a third friend, right? Sure? So by the distance, by the squaring rule, what is the distance from f to y? 2 minus 1 square. So what's that? 1. What is the distance from t to f? Square. So that this is 1, this is 1. So this total should be equal to 2. But what is the distance between t and y? What is that? 4. So this y to t is 4, but y to f is 1, f to t is 1. They are not adding up, no? Not adding up, right? So the second method is a problem. The first method is really the correct one, right? Sure, it is really the correct one, but there is a problem in that. The problem in that is that if you define distances by squares, then there are some statistics that you can easily derive mathematically. You can derive, for example, t distribution, you can do a estimate a regression line, and so on and so forth. If you do it with distances like median, then you can't you can't solve a lot of things analytically, but you need computers to solve it, right? And in the 17th century, when people were thinking about it, people like Gauss and others, right, who were much more capable than us compared to maths, still went on the squared direction because they did not have this, right? So we'll think of distances as squares, right? There's a lot of statistics now which deals with distances as median, as absolute values, right? Okay, they are called mad statistics. Why mad statistics? Because they say minimum absolute deviation statistics, right? Minimum absolute deviation statistics, which will come to that, right? There are called quantile regressions and other things which we'll deal with, but currently we'll only deal with distances as squares, right? What we will do is, in order to overcome this problem, yeah, Pallavi? Is this clearer now? Am I clearer now? I think let me just adjust my mic accordingly. Can you be a little louder, Pallavi?
Yes, actually, I think I just understood the point you mentioned about taking the absolute
So what I was saying was that intuitively the correct approach is to think of distances as absolutes, right? But you can't solve a lot of problems analytically on paper if you think of distance as absolutes. You need to use computers to answer many questions by doing simulations and other things, and people in the 17th century did not have access to computers, so they thought of distances as squares in statistics as the second best solution. Yeah? Hello? Hello? Am I audible? Okay, so now the problem with the squaring was that this plus this to this and this to this was not the same thing as this to this. So they are saying if you add this distance is 1, this distance is 1, so the sum is 2, but this distance is 4. There is a problem, right? So they thought of a simple way. They said let's take a square root again on that. Right? So let me do x1 minus x2 square plus y1 minus y2 square and take a square root. If you have done it 12th standard, they'll tell you the norm of a vector is that, right? But there's a lot of jol japata in that norm of a vector, right? All mathematics, all statistics is some construct to think carefully. Yeah. Oh, the meeting jumped? Okay. Oh, you lost your network, trying to reconnect. Anybody saw the network anywhere? It lost there. Yeah, now everybody can hear me? Am I audible now? Yes, Sachin has given me thumbs up. So essentially the idea is we come to a very important point. I am sharing my screen again, right? This is a very important point, so I will go back to it. Yeah? So the point is that I was trying to make is that thinking of the absolute difference is the right way to think of distances, right? In which case you will not have a problem. 2 minus 1, you get 1, absolute number. 3 minus 2, absolute number 1. 3 minus, so this will be 1 plus 1, 2. So 3 minus 1, absolute number is 2. And they would not have any problem. Currently in our square definition we have a problem. Right, because 2 minus 1 square is 1, 3 minus 2 square is 1, this is 1, this is 1, but 3 minus 1, 2 square is 4. So this plus this is becoming equal to 4, right, and you are not adding up. So 2 plus 2, 1 plus 1 is 4 in my way definition, right, okay. So there is a problem. So they thought of a way of solving this problem. They said, okay, let's add the 2 and then take a square root on top. So that will kind of bring things down. एक पहला तो sin किया तो उसको undo करने का sin, right? Okay, take a square root. Sure, right? If you have done any 11, 12 standard maths, you will know there is a vector, right? The norm of a vector is essentially that number, right? And then I was trying to joke saying that actually, yeah, Pallavi. So the idea was that actually there is a lot of mathematics is never something which is concretely given. It's the way people think in order to solve a problem, right? Okay, these are all mental constructs. They have their own limitations, strengths. If you try to improve on one side, you lose on the other side and all that, right? So this is what we have, right? Is the idea clear now? Okay. Now I am going to introduce to you another concept called the variance. I am sorry, everybody knows the variance, but let me look at it in a little bit on this context, because I want to prove to you that the variance is nothing but a mean only. Okay, it's nothing but an average only. You have been taught in descriptive studies that mean is one thing, variance is another thing, measures of standard, whatever measures of central tendency, ऐसा कुछ नहीं होता है. I'll tell you why. Sure, कुछ भी तुम लोग का मामा बनाते हैं. Okay. So now, okay, let me ask you a question. This is, now let me kind of change this a little bit, right? Okay. Okay, so you have a road, right? You have a road, right? The road milestones called 1, 0, 1, 2 and 3. Sure? At milestone number 2, there is a big, beautiful banyan tree, right? And banyan tree shade can be very cool. Yeah, it's very cool inside a nice old banyan tree, right? Sit under it, you will feel cold, right? Okay. So, 3 of you on a Sunday morning like this, right? Instead of attending my boring lectures, go to this banyan tree. There are 3 of you, right? One of you decides to explore what's around and walks up to this point, right? Walks up to this point. So let me mark this point in yellow, right? Another person walks up to this point, yeah? And the third person here says, I'm not come here to walk, right? I've come here to go to sleep, right? So this third person goes to sleep here, right? Okay? So all 3 of you came under the banyan tree. Somebody dropped you in a car. One of you started exploring and went up to point 1 and sat down there. Another person went up to point 3 and sat down there. And the third, somebody like me who said nothing doing, we have had nice Sunday ka lunch. It's a nice cool shade, I'm going to go to sleep here. So straight away snoozes off under the tree, doesn't go anywhere. Now, if I ask you the total distance travelled by the 3 of us, what would that be? What would be the distance travelled by the first person? 1. But in this case, you will call it 1 minus 2 square, right? Sure? Our distance formula. Distance travelled by the second person is 2 minus 2 square. Plus the distance travelled by the third person is 3 minus 2 square. Right? This is the total distance travelled by all 3. Right? Sure? Okay? Yeah? What is the average distance travelled by the 3 of us? Divide by 3. 3 of us walked this much. The average amount walked is divided by 3, right? Sure? Now, I am going to rename these numbers, right? So, 1 will become x1, right? 3 will become x2. Yeah? Sure? So, I am now going to change these numbers from x1, this becomes x2, x3, sorry, I will call this x3, okay, because that is the third number. And this 2, I will also call x2, right? Sure? So, I get x1 minus 2, I am just replacing x2 minus 2, x3 minus 2, correct? Now, you also know that 2 is the average of 1, 2 and 3, right? Okay. So, I have renamed it to x bar, right? X bar, right? X bar, correct? So, what do I have? I have x1 minus x bar square plus x2 minus x bar square plus x3 minus x bar square upon 3. Average distance from the mean, which is called the variance. This is the formula for the variance. So, the variance is nothing but an average. You have a set of numbers, then the variance of that numbers is the average of the distances from the mean. Right? Got this? And because it's an average, it's a sample average, as the sample size increases, the sample variance will also get closer and closer to the population variance. Right? So, the law of large numbers again applies. So, the sample variance, the variance is nothing but a mean. Got this? Sure? Right? The variance is nothing but the mean only, but a mean of different things. It's a mean of the distances from the mean. It's a mean of a average, it's the average of distances from the mean. So, greater the variance means greater is the average distance from the mean. Smaller the variance is, smaller is the average distance from the mean. So, if you pick up a random observation, If the variance is large, you would expect that random observation to be away from the mean. If the variance is small, you would expect that random observation to be closer to the mean. But the idea is that it's again a mean, right? So the weak law of large numbers again holds, right? And says that the sample variance will also now get closer and closer to the population variance as the sample size increases, right? That's why it's such an important theorem and applies to means. Everybody gets this beautiful thing? Variance samjha? I'm not going to bother to ask you to calculate variances, but I'm going to show you some example here in Excel and take you to the next most important concept of a covariance, which is something again critical idea in statistics, right? Mean, variance, covariances, correlations, covariance matrices, covariance structures. That's what really everything is, right? Because in statistics you want to understand movements between variables, right?
Why is it called weak?
Because there is another strong law of large numbers which makes even stronger assumptions, right?
About the assumptions.
Yeah, it's about the assumptions. Yeah? Check for, if you have Google, check what is the weak law of large number, what is the strong law of large number. This is a strong law of course, the moment I say weak, there must also be strong, right? So find out if there is a strong law of large numbers and what it says, and check with the weak law of large numbers and what it says. Do you know what sampling with replacement and sampling without replacement? If I am taking a sample size of 1000 people, and if Pooja is included in one sample, next time when I am doing the survey, again collect a new sample, I don't allow Pooja to be in the sample, then that's sampling without replacement. If I say it's okay even if Pooja's name comes up in the sample, she's allowed to be in the sample, that's sampling with replacement. Right? We are going to do sampling with replacement. So basically what this does is, if I now ask why, yeah? So this taken a sample of size 5. The first outcome was 1, it chose 1, second was 1, minus 1, minus 1, 1. Right? Sure? Got this? You get different numbers, right? Because all of you are choosing different random samples. This time I did 1, 1, 1, 1, 1. All ones. Right? I get a 1, 1, 1, 1 minus 1. So are you all getting this? Right? Okay. So now, let me find the...
So one thing.
Yeah, Pallavi.
So I was like, why is not like was
I am asking it to print the data, no?
it's always
Show me the sample, right? Because all this will be put into Y, and Y just the sample chose it.
so minus
Yeah?
what's that?
So now let me calculate the mean. Okay.
So did it really pass by the light research
So you see minus 0.2, right? 0.2. Right, I keep on getting this number, plus 0.2, minus 0.2. Right, why will I always get plus 0.2 or minus 0.2 in these examples?
then I was making it's not
There will be either 3 ones
something.
and 2 minus 1s, or 2 plus 1s and 3 minus 1. That's the only possible thing, right, in this. Right, but if I can of course get 1 pluses and all that, so that also can be a different, right? But in general, you will get plus, so just keep on playing around with this. So minus 2, minus 2, minus 0.6, minus 0.2, 0.2, 1, right? So are you you understand this point, how the sample mean is a random variable? Population mean is not a random variable. The average of 1 and plus minus 1 is 0. But if I take a sample of size 5, if I keep on taking different samples, I keep on getting different sample means. Right? Sure? Okay? Right? Okay. Now, suppose I increase the sample size. Increase the sample size to some number 5 lakhs.
This other trick, he said it.
Okay?
Mr.
Now do it and tell me what happens.
Mr. May equals getting. It's getting to the 0 1.
You're getting some number closer to 0.
Yes.
The sample is now closer to 0. Is it exactly 0?
So,
It's closer to 0. Right?
That's one sir.
Sure? You see the weak law of large numbers operating,
definitely.
and the point is, you know, so that Vijit, the point is, if I keep on increasing this, I can get it as close to 0 as possible. So I can make sure any circle of any radius around 0 will have some number of some element of x bar. As the sample size becomes larger and larger and larger. That's really convergence, right? That's really the, so you'll call 0 the limit point in maths, right? You have a sequence.
Yep.
x1 bar, x2 bar, all these are sequence of sample means with a certain, as the population size increases, the 0 is a limit point of that sequence. That is really the weak law of large numbers.
Right.
So it's now closer.
Now, it was get
It takes some time, I'm sorry.
the file and
Yeah, right? It's getting closer and closer. Right? Now, what I'm going to tell you is, set this number back to 5. Okay?
1. When
Yeah? What I'm going to do is, I'm going to take a sample of size 5.
you sugar,
Okay? Calculate the sample mean. And keep that sample mean somewhere. Store that sample mean. Then again take a sample of size 5. Again take the sample mean, size 5 again. And keep on doing this say 1 lakh times. So I'll get 1 lakh values of x bar, all of sample size 5. I'm going to look at what is their probability distribution.
something good time.
Right? And that will be very instructive. Right? So let me try to zoom out. So first I'm going to do this 1 lakh times. Right? So we must find places to keep these 1 lakh things. Every time I buy a new Kolhapur check, I'll have to find a place for it. No? I have 35 now. Right? So now let me create these places. Right? So what shall I give it? Place? Okay, place. Okay, so what will place do? Place will create a column which has zeros 1 lakh times. Right? Now I'm going to do a loop. I is equal to 1. Don't worry if you don't understand the coding here. Right? Yeah? Then I do repeat, I open the loop.
Top.
Right?
Look button.
I put it in the ith column of place I. Right, so a square bracket means in the I is equal to 1, so first column of place I is equal to 2 and so on. I is equal to I plus 1. If I exceeds 100,000, break. Right? This is unnecessary, yeah? Just right? So what do I do? I is equal to, so first I have a place column which has 1 lakh values. I is equal to 1. Then it takes a sample of size 5, calculates the mean and puts it in the first column, first row of place. Then what does I become? 2. It again calculates the sample mean and puts it in the second row of place. I becomes 3. Calculates sample mean, puts it in the third row of I. So basically think of place as an empty shelf, 1 lakh dots. I is equal to 1, put in the first shelf. I is equal to put the second shelf. When you keep on doing this, till all the shelf has been filled. Right? So let me now run this. Yeah, so now if I say place, Yeah, I've got this 1 lakh values, right? Yeah? Sure? Now, if I take the mean of place, I got a small number, 0.028. And the variance of place, I got a number 0.20. Right? Sure? What does it mean? It means, okay, so calculate the mean and the variance of place now.
So you are expecting that this spot is 1 lakh times, right?
Yeah, 1 lakh times.
Then it's up to 1 lakh.
Yeah. And then you have to do mean of place, variance of place. Okay? Or standard deviation of place. Standard deviation, if you take the variance and put a square root. And you know why you have to put a square root? No, because the distance ka jara jol dapata hai, the square root. Right? Sure?
But then I extend from I equal to I plus what is
So basically, Pallavi, think of a, so we have to do this 1 lakh times, right? Yeah, our basic problem is that we have to take a sample of size 5 and calculate the sample mean 1 lakh times, correct?
Yeah, right.
Okay, so if we have to do it 1 lakh times, then we have to remember all those 1 lakh numbers, we have to keep on jotting them down somewhere, no?
Okay. So,
So you need to first create place and then keep on putting them in those places, right? Now, keep on doing this and tell me what is the mean of place and what is standard deviation of place.
Mean is 0.0014 seconds and standard deviation is 0.427.
Okay. Now actually if you want to do this, just round this mean, right? Round the mean to 2 places. So that you don't have too much of a clutter. And round the standard deviation also to 2 places. Save the clutter, right? And make it easier for you to see the points. Now if you do the mean and the standard deviation, what do you get?
Mean is 0. Standard deviation is 0.4.
Standard deviation is 0.45. What do you mean by mean is 0? So it says that even when each sample mean is different from the population mean, the average of all sample means equals the population mean. This is a very famous property in statistics called unbiasedness. They say that the sample mean is an unbiased estimator of the population mean. That is, even when each sample mean is different from the population mean, the average of all sample means is 0. Is exactly the population mean. Right? You see the point? It's called unbiasedness. But of course, each sample mean will be different from the population mean. There will be some average distance from the mean, which is the standard deviation. Yeah? Understood the idea of unbiasedness? So unbiasedness, why is it unbiasedness? It says, okay, each time there is a mistake, but that mistake is not systematic overestimation or underestimation. On an average, you are still correct. So the mistake is only because of the statistical chance, right? Sure? That is why we look for unbiased estimates. And okay, even if I have a sample of size 5, I still have an unbiased estimate. If you reduce the sample size to 2, will I still have an unbiased? If you reduce the sample size to 2 and see what happens. Reduce the sample size to 2.
and what was the sampling error so clearly at the accelerator?
See what happens is, yeah, that's sampling error, Pallavi. So it says each time we'll have a sampling error, but the sampling error will not be systematic sampling error. Yeah, so you're not sure whether it's overestimation or underestimation. So like a coin, when you toss it, you don't know whether it's +1 or -1. Sampling error exactly a random variable like that with mean value 0. That's why regression you write error term and all that, right? We come to all that. Sure? Is this clear? Everybody gets this idea? Yeah, Pallavi?
Sir, sir.
And last year, it's a family one.
Pallavi, be a little bit closer to your mic today. Today your voice is a little bit down.
This is the open.
Yes, right, I'm cool. Well, it was like the custom stuff.
No. आपला माईकचा आवाज व्हॉट्सअप आहे ना रे?
Okay.
Yeah, now you're much better. Now you're like usual, Pallavi. Yeah.
Okay, so I'm getting 0 for business point for
Yeah, so 0 is the mean of all the means. So it says though each sample mean will be different from the true population mean, the average of all the sample means will still equal the population mean. It does not mean that you take many samples, it just means that in any one particular sample you take, you know that there is a sampling error, but that sampling error is not a systematic sampling error. So you are not overestimating or underestimating. It's a sampling error which will on an average either plus or minus. That's bound to happen in any statistical experiment. But your method has got no problem like systematically overestimating or systematically underestimating.
So, and then what I want is to well, check.
What about the
Well, really quick.
2? So all that I'm doing is I'm rounding up that mean. No, it was giving 5, 6, 7, 8 digits earlier. No. And you would not have believed that it actually is 0. So when I make it round up, it becomes easier for me to teach because you actually get 0.
Okay.
Yeah? Sure? Now, change the sample size to 2 and tell me what happens.
Certain mean is same, but the standard deviation increases.
The standard deviation has increased. The mean remains 2. The mean remains 0. But the standard deviation has increased. Right? The point is, however small the sample size is, the estimates are still unbiased.
You do.
Right? However small the sample size is, the estimates are still unbiased, no? Even if I take a sample size 2, on an average I am getting the true population.
Right.
So sampling error will not become systematic because you have a small sample size. But your estimates are wider off the mark. The standard deviation is large now, right? Now suppose if you increase the sample size to 200, see what you get.
Just like in watch it. And look at them.
Standard deviation is increased.
Standard deviation has decreased, right? So your estimators are closer and closer, are spread closer and closer around 0. Yeah? If you make it 2000, see what happens.
At that time.
They can invest. You have turned it up. We are going to
Yeah, I know, even my computer is very old. It actually has got archival value because I realized that actually when Shaiste Khan had come to Pune, when he left, he forgot the laptop here. That is the laptop that I have now. Right? It's an old laptop, but you can. Okay, so make it say 500.
my
500. It's even closer. So what it means is, so there are two things. One is the sample mean is always an unbiased estimate of the population mean, no matter what the sample size is. The sample mean is always an unbiased estimator of the population mean, no matter what the sample size is. Even if sample is very small or very big, for the unbiasedness property, sample size does not matter. But if you want your estimates to get closer and closer to the true population value, they'll be on an average correct, but you want them to be the errors to be small. If you want them to be get closer and closer to the population value, right, then you need to increase the sample size.
Yes.
In fact, when estimators get closer and closer to the true population value, as the sample size increases, they're said to be consistent estimators. right? So consistency of an estimator is definitely has to do with the sample size. So consistency is said to be a large sample problem. Whereas unbiasedness is no sample size. Some people call it a small sample property, but actually it holds even in big samples, right? So it is maybe all the sample size. Right? Sure. So with kappa I can see this more graphically. Because I've got continuous variables, I've got discrete variables, then I can do a nice graph. It looks like just push me. Right? But I do something else and will come back after the T rate to get this, right? And then it so set adjustment is in. So we'll have a tea break for 15 minutes. Lab. Right? Today will be a lab. For learning is unbiasedness, consistency. We'll do experiments on our own, etc. Right? Just like chemistry, etc., biology, you can do experiments in economics as well. So we'll do a lab now. Okay? Right. So install two libraries. Library ggplot2, library dplyr. Yeah? Okay? Right? Now x is equal to R norm. Right, so what is x? X is random variables that are normally distributed with mean 0, standard deviation 1. And how many of them are there? 1, 2, 3, 1 lakh random numbers. Can you hear me? So x is 1 lakh random numbers coming from a normal distribution. Okay. I think maybe I'm not sharing it. Yeah, I'll do that. Thank you. Is it now, Pallavi? Okay. So now what is x? You install these two libraries. X is nothing but 100,000 random numbers coming from a normal distribution mean 0 and standard deviation 1. Change the mean, you'll have to do this, right? Change the standard deviation to 2, you'll do this. So I'm keeping it like this. First, I will draw the graph, right? Right? So let me kind of say, so this will create a data frame called x, okay? And say P1 ggplot data AES x is equal to x geom understroke density, right? Let me first see whether this runs, okay? Yeah. Right, so what does it do? It tells you the density of x. It gives the probability distribution of x, right? Density, just to make you feel nice. Just kind of keep you interested. Right, so if you do this, you get this picture with the pink in the middle. Yeah? Right? Everyone is getting this picture?
So can you show the code once? Okay.
Yeah, folks? Okay. Now what happens if you change this alpha from 0.4 to 0.9? Yeah. The opacity of the, right? You read something like this, much more darker, right? Yeah? Yeah? So what is this graph telling you? What is the mean of this random variable? 0. But not each value of the random variable is 0. Take values as low as minus 2.5, as high as plus 2.5 and above. Yeah? Right? Sure? The area of the entire curve is set to 1. So the probability, if you want to find the probability that this variable takes values between minus 2.5 and 2.5, you just have to take the area of the curve between minus 2.5 and plus 2.5. Because the entire area of the curve is normalized to 1. Right? If you've done a little bit of maths, you will know that there is a formula, no? 1 upon root 2 pi e raised to minus half x. So 1 upon root 2 pi converts that to 1. Makes that area equal to 1. It's a normalizing constant, right? Okay, but let's not, right? So basically this is 0, this is the mean, and this is how now try and change the mean of this from 0 to say 2, see what happens. If you change this from 0 to 2, what happens? What has happened if you change this from 0 to 2? Yeah?
It will be centered around 2 instead of 0.
So this whole thing shifts horizontally. The whole topi shifts, no? Think of it as a joker's hat or a fireman's hat. Right? So we just push the fireman's hat away. Right? Sure? If you change the standard deviation, what happens? If you increase the standard deviation, what happens? Change the standard deviation, see what happens. Just play around. Yeah, Pallavi, I can't hear you. You need to be a little louder today.
Yeah. Yeah, so can I share my screen?
Yes, please do. Yeah, show me. So run this and see what it does. So, yeah, so what's the problem, Pallavi? Pallavi, there you need to type P1 again, no? In the console, because it has gone into an object called P1. Now go to console and type P1. Go to console. Run, select it and run. Select P1, no? Again, yeah? Sure? The reason is, Pallavi, that when you say ggplot and put into an object called P1 RS, put it into P1. But if you want to see P1, you have to call it, and don't call it in the editor. You can call it in the console down below. Yeah? Sure? Okay. Yeah. So if you can stop sharing now, I can begin sharing. Are you guys getting this? Now keep on playing with the numbers, keep on playing mean, standard deviation, change it, and what do you get?
So the spread increases if I increase the standard
Yeah.
deviation and decrease
Okay, so basically the shape changes if I change the standard deviation, the location changes if I change the mean. So mean is a location parameter, standard deviation is the shape parameter. Any probability distribution will have two things, no? Right? Location and shape. In some cases, there might also be a skewness on one side or other side, right? But in this case, so it's a basically when you specify the mean and the standard deviation, you distribute the distribution completely. So it's a two parameter family of distributions, right? It's a two parameter family of distributions. Mean and standard deviation, if you describe the whole distribution completely. Correct? Okay? Right? So a particular normal distribution will depend upon two things. One is what's it mean and what's its standard deviation. Right? There are also things called skewness, where the distribution of one side or another, but for a normal distribution it's zero. And there is something called kurtosis, how peaked the distribution is. Right? For many distributions, you have to describe skewness, kurtosis, mean, standard deviation, all that. There will be more complex distribution. This is just a two parameter family of distributions because the skewness is 0 and the kurtosis is fixed at 3. Right? Sure? So is everybody getting this? Okay, now what I am going to do is, I am going to now take, okay, this is x, right? Okay, I am going to take a sample of size x, right? Okay. हॅलो मी एका लेक्चरमध्ये आहे जरा उशिरा फोन करा या I take a sample of size x, right? Okay, sample from x of size 500. Replace is equal to true. Okay, right? Replace is equal to true. Okay, yeah. Then what I am going to do is, so I am going to call it data 1 dot data 1 is equal to data dot frame y. Okay, sure. And now right, there is a variable called y, right? Okay, and so I will call this green. Yeah? Okay, so what is now y? It's a sample of size 500 coming from a normally distributed random population. The population mean is 0, the population standard deviation is 1. Correct? Yeah? Population standard deviation is 1, population mean is 0. I am taking a sample of size 500 from this population, right, with mean 0 and standard deviation 1, and I am now looking at the yeah, right? Compare the two distributions. What is the difference between that earlier one, call it P1, the previous one? So call this P2, right? Let this be data x is equal to x, and this is pink. Yeah? Right? Now, play around and tell me what are the differences. So, I have taken a sample of size 500 from this population and I am plotting the probability distribution of that. Compare the two. Compare the two and tell me what you learnt.
This one is not as normally distributed.
Okay. But what is the mean here? It's centered around 0. And what is the spread? Is it more or less than the previous one? It's more. Right? Okay. Now increase the sample size from 500 to say 5000 and see what you get. The spread is less, right? So values are lying closer and closer to the true value of the mean. If you increase it even more, lesser, right? And the shape becomes closer and closer, right? So the sampling distribution gets closer and closer to the population distribution in this case as the sample size increases. So sample mean will get closer and closer to the population mean. The sample variance will get closer and closer to the population variance, and so on, right? So, but whatever the sample size, the mean of the sampling distribution is still the same as the population distribution. That is unbiasedness. But as the sample size increases, the variance keeps on falling, right? That is consistency, right? That is consistency. Sure? Are you guys getting this? Okay, now we'll do a little bit more difficult job, right? What I'm going to do is, okay? Look at the sampling mean. Okay, so what I am doing, I am taking a sample of size 50, calculating the sample mean, doing this 1 lakh times and generating the probability distribution of the sample mean, right? Sure? Okay? आ गया? What do you now see? At that point, we are now calculating the probability distribution of the sampling mean, which is called the sampling distribution of the mean. We have the population variance, population data, population distribution, and then we have the sampling mean distribution, which is called the sampling distribution of the mean. Right? The idea of sampling distribution is clear to everybody? So what is happening now? More spread, right? Okay, sure. Actually, I can show you something. I wish my computer had that computing power, but let's see if Shaiste Khan was actually using computers like me. Okay. I hope this works. Huh? If it doesn't work, yeah. As usual, I'm a champion at making silly mistakes. I'm the not Pune champion of silly mistakes. Hey, only the green. No. Where is a bracket expected? Okay. Yeah. Yeah. Okay. Okay, now this is what I wanted to get, right? Let me now select all that. No. This is not doing the correct thing for me. Okay. Now I am asking you a question, right? You get, so basically the yellow is the original probability distribution of the data. X bar, X is the sampling distribution, the sample size of 5, correct? Yeah? 50. Sure? Please understand the important question. What am I doing? I have a population, 1 lakh values, mean 0, standard deviation 1. Yeah? I want to estimate the, suppose I don't know this population. I want to estimate the mean of this population. I take a sample size of 50. Calculate the sample mean. Okay? I keep on doing this repeatedly. I do this 1 lakh times. So I have 1 lakh times sample means. I am plotting the probability distribution of sample means in the pink color. The original population distribution is in yellow color. Right? Okay? I want you to first tell me, observe these graphs and tell me what your findings from these graphs are. So here we have. Right? So the pink distribution, the distribution sample mean is, so both of them have the same mean, 0. The sampling mean is same as the population mean, but the variance of the sampling mean distribution is much smaller. Right? Just see what happens if you keep on changing the sample size. Change the sample size to 1, see what you get. Change the sample size to 5, see what you get. Change the sample size to 10, see what you get. And keep on playing, and then we can discuss this. Ah, the code. I thought you would have learned the code by now. Come on, I've taught you to bake a cake. You don't need to read the recipe every time now. Play around. Change the sample size to 1, see what you get. Change the sample size to 10, see what you get. Change the sample size to 50, see what you get. Change the sample size to 500, see what you get. Don't do beyond 500. Your laptop will explode. Then you must wear a fire mask and all that. But if it is 1, then what do you get? When you take the sample size of 1, what do you get? Sample mean is based just on one bit of information. What do you have? We are going to come to a very fundamental idea going to be required in the class afterwards. If the sample size is 1, then both the distributions coincide. Now keep on increasing the sample size. Keep on increasing the sample size and see what you get. Yeah? I want everyone to understand that. If you increase sample size, what happens? Does the mean change? Yeah, so even if your sample size is 1, you're still unbiased. But if you increase the sample size, the variance of the sampling distribution gets closer and closer to 0. So all the values of the sampling distribution lie closer and closer to 0. Right? So if you take, the point then is that if you take 0 and define any circle around 0, then you can raise your sample size sufficiently so that the entire distribution is in that circle. That is exactly the property of consistency. So the sample mean is an unbiased as well as a consistent estimator. Is everybody getting this? The sample mean is an unbiased and a consistent estimate. The variance of the sample mean falls with the sample size. Right? Okay? Is this clear to everybody? Unbiased and consistency is absolutely clear. So these two properties any estimator must have. So if you are estimating a population value based on the sample, the first property it must have is unbiasedness, that is, there must not be any systematic bias. And secondly, it should have the property that as you get more and more and more information, your guess must lie closer and closer to the true value. That is, it must lie around a smaller and smaller and smaller circle around the true value. It might not be ever exactly equal to the true value, but it can get arbitrarily close to the true value. Right? Limit points of a sequence really. That's the definition, right? Okay. Sure? Is this clear to everybody? Consistency and unbiasedness? Okay. Now rack your brains and tell me why the variance of the sample mean falls as the sample size increases. हाहा, मैं बोलूंगा नहीं, आप सोचो पहला. The question, Pallavi, is why does the variance of the sample mean fall as the sample size increases? This is one of the most important findings that you will learn, and I don't want to tell you like that. I want you to earn that understanding. Rack your brains. Rack your brains for some time. You saw that, no? If the sample size is 1, the sampling distribution coincides with the population distribution. Sampling mean coincides with the population distribution. As the sample size increases, the mean remains the same, but the distribution of the sampling mean becomes, so you become more and more accurate about your estimate of the population mean. Right? I would rephrase it a little bit. She is by and large right. Can you rephrase her statement or give a different point of view, whatever? Is there any other point of view that you guys can offer?
More the sample, more it will average out to 0.
Try. I don't have any guns, so I'll not shoot anybody. So even if you're wrong, that's perfectly fine. Because the population variance is already there, no? The point is the sampling variance is smaller than the population variance and keeps on becoming smaller as it increases. Your point is right, but we need to kind of little differently. Anybody? Take another try.
So when we have no sampling size is 1, so our value can lie anywhere in that whole thing. But when we take a group of values, then they average out little closer. The average comes little closer to it.
He's right. I think what is happening here is, think of this class as a population. Right? I want to find what the exact time is. So I ask him. I ask anybody chosen randomly, but just one person I ask. So you can be that one person, he can be that one person, she can be that one person, he can be that one person, she can be that one person, she can be that one person, she can be that one person, anybody here can be that one person. Right? My estimate is just what I hear from that one person. So what will be the variability of my estimate? Exactly that of the population, because anybody in the population can be that one person who I am going to believe. Right? Sure? Is this clear? All that I am going to see, I am going to ask, Kitty Wajle, Vijit says 1255, I said 1255 is the estimate. And I can ask anybody, any one person randomly. So my estimate will be exactly as variable as the differences in your time. All of you are the population. The time in each of your watch is really the time in the population. So if I am using just one data point, the variance of my estimate will be the same as the variance of the population. Because any one person can be that, no? Right? If I ask, if I randomly pick up Vijit, I'll get a number on Vijit as my estimate. If I ask Pooja, pick Pooja randomly, the time on Pooja's watch will be my estimate. Like that, anybody can be asked. If I ask Amita, then that will be the time on her, right? So anybody can be asked, so that my estimates, the variance of my estimates will be exactly equal to the variance of the time in the population's watches. That's why when you take the sample size 1, the sampling estimate coincides with the population. Now, if I say now that I am going to, so basically remember, the variance of the estimate is a measure of imprecision. If the true value is 0 and my estimates are here and there, the more imprecise, right? Now, suppose I say, nahi yaar, ek ko nahi पूछेंगे, दो को पूछेंगे. So I pick up any two of you randomly and then form an average. How many bits of information I am now using? 2. Previously, how much was I using? 1. So now if my information is twice as previously, the precision must also be twice. So if by using 1 bit of information, my inaccuracy was sigma square, now it should be sigma square upon 2, because I am now using 2 independent, I am using more information, right? If I ask 3 people, sigma square upon 3. If I use n people, sigma square upon n. So if I have a population that is normally distributed with say mean 0 and variance sigma square, if I have a population that is normally distributed with mean 0 and variance sigma square, and if I take a sample of size n, then the sample mean will also be normally distributed. It will have the same mean as the population mean, but its variance will be the population variance divided by n, sigma square upon n. Clear? Because I am using n times more information. And as n tends to infinity, sigma square upon n will become smaller and smaller and smaller. So your estimates will come closer and closer and closer. Is everybody getting this?
Is the standard error
The standard error is the standard deviation of the sampling distribution. So sigma square upon n is the standard error. Right? The standard error will keep on falling. Right? Right? Sure? Because I use more and more information. Right? So suppose if I am giving you an estimate and you think that the estimate is based on a sample size which is too small, how will you criticize that estimate? What will be your critique of that estimate? Will you say that this is biased because the sample size is small? No. Right? Because even if you have one data point, your estimates are still unbiased. Your errors are large. Sure? Okay? You will say that this is inconsistent. In the sense, you will say that this is likely to be unreliable. This estimate is likely to lie far off from the true value. So please increase the sample size so that the accuracy of the estimator improves. There is a difference between accuracy and bias. Right? Whereas if you think that the sample size is not randomly selected, even if it's a large sample, it's not really randomly selected, right? Sure? So for instance, if you wanted to see, if you wanted to find out how long does it take by bus from Pune to Hatkanangle, right? And you actually went at a toll naka and kept on asking car drivers how long it took them, then you really have a biased sample, right? So even if you have a large sample, even if a small sample will give you biased estimates. So there is a problem in the sampling design, right? Okay, so there are sampling errors and non-sampling errors. Sampling errors are errors that arise even if you have good sampling, because sample means are likely to be different from population means. But non-sampling errors are errors where you ask people to travel by car when you want to find out how long it takes for people to travel by bus, right? That would be a non-sampling error. Yeah? Sure? Is this clear? And why? So the critical idea is that if the population, you have a population which is normally distributed with mean 0 or whatever mean, and standard and variance sigma square, the sample mean will still be normally distributed, as you have seen, will have the same mean as the population, but the variance of the sample mean will be sigma square upon n, assuming of course all those samples are random and everything, IID and all that. Right? Is this okay? Keep this in your mind because this is going to be important. We are going to understand Z distribution and T distribution and chi-square and F and all those as we go on. And then at some point I will tell you, friends, we need to junk all this because modern statistics we really don't need any of that. Right? Okay? But these are all legacy ideas. You have to learn them. Okay, because however much you know modern statistics, if you went for an interview, they told you what the T distribution, no idea, they'll not give you a job, right? Sure? So these legacy things we'll learn properly. Okay? Now I'm going to go back to Excel. Yeah? And tell you something very insightful. I mean, I call it insightful. I don't know whether it's useful or not. Hey. Okay. Right. So please pay a little bit of attention now. They're going to be very important. So you have X. Yeah? X takes values 1, 3, 2, 4, 5, 6, 7, 4, 5. Right? I want to calculate the variance of X. What do? I first calculate the average of X, right? Yeah? Right? Then I calculate a column called x minus x bar, correct? Which is A2 minus $A $11. Yeah? And now $A $11, my dear. Okay? Right? So what is this? This is 1 minus 4.111, 3 minus 4.111, 2 minus 4.111, and so on. Right? Sure? Yeah. And now if I sum this,
It is 0.
0, right? Very small to 0. Sum of the deviations from the mean are always equal to 0. Can you tell me why? Can you?
Positives and negatives will cancel out.
No, I want some maths. How do you know positive negatives will cancel out? It can't be an article of faith, no, Pallavi.
What's the question?
Why do the sum of the deviations from the mean always cancel out?
There are equal number of observations that are
Who told you?
Not necessary actually.
She says not necessary actually.
But if we have like small amount of numbers, then I don't think they cancel out. Like it will be closer to 0, but it won't be 0.
It will always be 0. That is the fun. Why is the question. And many of you always believe it to be 0, but none of you can prove it. Why do you guys believe things which you can't prove? How? This is not different from any. If you cut the comedy, then you will get some job or kind of a thing. Right. It's so simple. Can I tell you why? Okay? Okay, I'll have to go to word now again. Okay? Now, so think of xi as an ith observation minus x bar, right? Sure? x1 minus x bar, x2 minus x bar, like that. What is x bar? Summation of x divided by n, correct? Yeah? And this is x minus summation of x divided by n. Sure? Okay. Now I am going to sum this. Yeah? Right? Sure? If I sum this, what do I get? I got sum of x minus sum of x upon n, right? Now x bar is a constant. So if I sum in x bar n times, what do I get? N into x bar. X bar is a constant number. No, it could be 2, 3, something. Right? So what would I get? Sum x bar, right? Which is nothing but n into x bar. Yeah? So I have sum x bar minus n into x bar. Now what is x bar? Summation sum x upon n. So n will cancel. So I get sum x minus sum x, which is 0. Simple. Correct? Sure? So some of the deviations from the mean will always be equal to 0. Agreed now? Small b. So it is no longer has to be an article of faith, right? Niche upar. This is simple 5th standard math that if you do, you will get that answer. Okay. So now I am going to my Excel. Okay, so x, then the next step is to square these, right? Square, right? Sure? Okay, how do I square that? B2 star B2, right? I get this. Yeah? Okay, now I have to sum this and divide this sum by n minus 1. I will come to y n minus 1 in the next class, right? Y n minus 1, because you will have n numbers, it is what? It is coming from the deviations, no? Sum of all deviations have to be 0. So if you choose 9 deviations randomly, the 10th deviation has to be such that the sum equals 0. Right? If there are 10 numbers and the sum of the deviation 0, 9 deviations can be anything. But the 10th has to be such that the sum has to be 0. So there are actually 9 numbers which can vary independently. Independent bits of information only 9. Degrees of freedom are only 9. Right? So we divide it by whatever n minus 1. In this case, how much? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8 are my degrees of freedom. Right? 9 data points. Sum of all the 9 deviations has to be 0. So only 8 can be independently chosen. The 9th has to be chosen such that sum equals 0. So only n minus 1 degrees of freedom is there. Right? Sure? Okay, so the variance is this. Okay, it's the average of the squared deviations from the mean, but the average is n minus 1 because there are only n minus 1 independent ones. One of them is redundant. Any 8 you choose on your own, the 9th will then have to be fit in. It will have to fit in. Right? So folks who fit in have no freedom. If you have to fit in, you have no freedom, no? So only the remaining 9 folks are free. The 10th person has to unfortunately fit in, right? So we remove that. We don't call it free person, right? Okay? When you have to fit in, you don't have freedom. Yeah? Okay? Right. So you get this. Now, so what have I done? It's x minus x bar, right? Now think of it being x and y. Okay? There is a x and there is a y, right? Okay, and suppose x takes the values, okay, and y takes the values, suppose y takes the values like this. Okay, now suppose I am doing the following. I found both the means, right? Then I take x minus x bar first, which is E2 minus $E $11, okay? Yeah? Similarly, I do y minus y bar, okay? So each value of y minus the mean of y. Right, what should formula be? F2 minus $F $11, correct? Yeah? Now instead of multiplying x minus x bar into x minus x bar, like I did for the variance, I now multiply x minus x bar into y minus y bar. Sure? So multiplying x minus x bar into x minus x bar, right? So it's the same example if instead of y you had x only, then you will get the variance, right? Okay, now I am going to multiply the two. Yeah? So we now do G2 star H2, right? Yeah? And then I average this, I sum this, and divide by n minus 1, which is 8. I divide this by n minus 1, which is 8. Right? Now, do you see a parallel between variance and this number? Here I had x and y. Instead of y, if I had x, I had done the same thing, x minus x into x minus x square, I would have got the variance. Right? Here, instead of just having x, I have a x and y, and then I calculate the deviation of each value of x from the mean, each value of y from the mean, multiply, right? Okay. You see, the average I have got is positive number, 2.45. Why is it a positive number? Why is that average a positive number? Because most of the values in this column are positive. Yeah? Right? Most of the values in this column are positive, predominantly positive, so the average is also positive. Now, why are these values positive? Because what are these values? The products of two quantities. When is the product of two quantities positive? When the quantities have the same sign. So both quantities are negative or both quantities are positive? Positive, right? So for instance, here you find both quantities are negative and the product is positive. Now why this negative? Because this value of x, the first value of x, is below the average of x. And the second value of y, first value of y, is also below the average of y. So both the quantities are negative, right? Here both the quantities are positive. Why is it positive? Because 7 is bigger than 5.33, 8 is bigger than 7.44, right? So what is this really saying? This saying this number is positive because most of the times x minus x bar and y minus y bar have the same signs. What does that mean? That means that most of the times if x is above x bar, y is above y bar. If x is below x bar, y is below y bar. Therefore, that number is positive. That number is positive, it indicates that x and y are moving in the same direction with respect to their means. Therefore, that number is called the covariance. Right? When would the covariance be negative? If most of the time, if x is above x bar, y is above y bar and vice versa. The signs are negative. It will mean that most of the times, if x is above x bar, y is below y bar, both the quantities are moving in opposite directions relative to their means, you will get covariance which is negative. Right? And if some of them are positive, some of them negative, randomly it's 0, then there is no covariance. So covariance is telling you the direction of co-movement between the two variables. But covariance is not different from variance. Variance is what? X minus x bar into x minus x bar. Instead of here you have x minus x bar into y minus y bar. So if x is the same number, x and y are the same numbers, covariance will always be positive. That's why variance is always positive. Because no variable can move in opposite direction compared to itself. Variables are not schizophrenic, people are. Right? Numbers don't suffer from schizophrenia. But, right? Sure, tragically a lot of people suffer from schizophrenia. It's a very serious mental problem. Mental health is a very critical issue now, I think. And we should not, yeah. So you get this point? Why? What is the idea of covariance? Right? Sure? Let me ask you a question. How many of you are economics students? Economics. Most of economics students लाजायचं नाही हातवर करायचा कोण काय बोलत नाही. Yeah, I know मी पण कुणाला सांगत नाही पण वर्गात इथे ठीक आहे. We can always tell people, right? Okay, now if x were the price of apples per kilo and y were the price of oranges per kilo, Do you think they are complements or substitutes? If X is the price of apples per kilo, Y is the price of oranges per kilo in Gultekdi market on some 8-10 days. Do you think they are complements or substitutes? Why? So if the price of apples goes up, people substitute towards oranges, and the price of oranges, price if elasticity is a positive, cross price is a positive for substitutes, the negative for complements. So apples and oranges here are substitutes. Right? Sure? Okay. I'll give you one more example. Any doubts about what we have done today? Sure? One question I'll give you for homework. Okay? You must solve it by the next class and think how you do it. See, once you go back from this class, your school headmaster calls you. He says, see, you have been listening to these classes, I know. See, we keep a tab on what our students do, right? Even after you passed out of 10th standard, you didn't contact us. We have kept an eye on you. And we know that you're doing all this statistics course and all that, right? So we want your help. You say, what is the help that you want? So the principal says, see, Baba, you know our school is very good and we are dynamic and always trying to think of new things. But you see, my faculty don't always agree among each other. Amita will know how serious that problem is, right? And so we can't do anything. So what is the problem? He says, see, our faculty, all of us want our kids to do well and all of us want to do something. But there are at least 3 groups in our faculty. One says that students who are good at literature are not so good at maths. And so good at maths are not so good at literature. So let's develop comparative strengths of students. Those who are good in maths, let's teach them really high quality maths, but they don't need to know Shakespeare and all that. If they can write some official correspondence, sir, I am sick today, some sick leave letter, etc., that's okay. Whereas kids who are good in literature, let's not bother them with calculus and all that, right? If they can learn their bills and all that, that's fine, but teach them really good literature. Right? That's one school. Another school of teachers is what nonsense. Kids who are brighter than others are brighter in both maths and literature. Kids who are not brighter than others, below average, are below average in both the subjects. So let's find out kids who are below average and let's teach them more maths. You know, let's sit them, ask them to stay back after class, revise their maths and literature, and they will improve. And the third group of teachers is, we are being here for 25, 30 years now. What nonsense, there is no relationship between the two abilities. Some of them are very good in both, some of them are very bad in both, some of them are better in one thing, etc. So it's all randomly distributed, maths and, right? So we can't agree. So will you help me? Right? Will you help me? So what you do is, you say, okay, sir, I will come to class tomorrow. Don't call everybody, call a small number of randomly selected children. In this example, we call 10 randomly selected children. Yeah? Okay? Right? Okay, before that, okay, we'll call 10 randomly selected children, and then they are given a test in maths and a test in maths in literature. Right? So maths, and is a test out of 10 marks. Yeah? Right? The marks that they have scored. Okay? You have to decide by the time you come back on Monday which of the 3 group of teachers is right. And you have to explain on the basis of what I have taught you. Think, okay? Coming back to statistics, remember the covariance is also an average. Weak law of large numbers will work. The sample covariance will get closer and closer to the population covariance. as the sample size increases. Yeah? Now you know why the law of large number is so important? उसको निकाल लोगे तो पूरा statistics धपक, finished. There is no logic for statistics then. Which one? Yeah, maths में 9 मिला उसका out of 10. 9, yeah. One chap is not good. Thanks. Yeah. I can tell you the name of this student who's currently teaching you, but forget everybody. So you have to answer this question. How will you answer it? What will you do? You want to answer one of which of these three groups of teachers is right. I have already given you the tool. कैसे करोगे? अब correlation अभी सीखा ही नहीं अपन ने. We have not heard of that. Covariance, right? Covariance will tell you what? Which direction they move related. So first group of teachers which says students who are bad in maths are good in literature and all that, what should be the covariance? Negative. If you calculate, find it negative, first group of teachers. If you calculate covariance and find it positive, second group of teachers. And you find it 0, third group of teachers. You are estimating a number, right? It has to be, so this is not a population number, that's a sample number, but we still will look at that, right? Sure? So we'll be able to do it in the next class. Any questions about what we did today? Yeah? Unquestionably clear? Okay, right. So if you know covariance, if you can give me the right answer, next class we will do two things. One is the test that we did last time, right? And will you show them how to do it? Will you send me your results, I'll look at that. And then we can, if that's fine, then you show them how to do this. And secondly, we will now start learning about tests of hypothesis. T-test, F-test, Z-test, and when to use what. When to use what? Yeah? Okay? And then we can go on to regression. And then I'll tell you why it doesn't work. Right? Okay? Then what you should do. Right? Okay, thank you folks. So have a good day, good weekend, whatever remains.